Hey everybody, thanks for joining us for our iMAPS technical meeting. Matt Bracey, I'm the president of iMAPS New England chapter, and we're here with Rajiv Iyer today. He's going to be giving a talk on process development and sustainability of fine volume adhesive jetting in microelectronics. I just have a few announcements to make, and I'll pass the microphone over to Richard Holman. First announcement is our business meeting. Our annual business meeting will be next month, June 23rd at 5 p.m. And we are going to be featuring Professor James Eakin of Worcester Polytechnical Institute. And he's going to give a talk on how WPI managed to survive and flourish during the COVID-19 pandemic and what that organization did to make things work. Also, the SMTA Boston chapter is going to have some upcoming webinars. They're on Thursday, May 13th, which was last week. So never mind. I'm sure you get more information from them though, as far as that goes. And then finally, all of our sessions that we've done this year have been recorded and are on our chapter YouTube channel. If you can't find the link on our website, you can feel free to email me or reach out to anybody on our board and we'll be glad to help you. That's all the announcements I have for now, and we're going to pass it over to you, Richard. Thank you.
Hey, thanks, Matt. So our speaker tonight is Rajiv Iyer. He graduated with PhD in Industrial and Systems Engineering from State University of New York at Binghamton, with research focused toward microliter and nanoliter deposition using jetting systems in surface mount assembly. He has more than 10 years of experience in the Electronics Manufacturing Center as a senior process engineer for the Camelot Dispensing Group at ITW, and is currently program manager at Medtronic in the greater Boston area and has been in the medical device industry for almost 3 years. So with that, I will pass it over to Rajiv.
Thank you, Rich. Thank you, Matt, for the opportunity to present at iMAPS. I'm just going to share my screen here and we can get started shortly. Yeah, just let me know if you can see it.
Yes.
Okay, thank you. Yeah, thank you for giving me the opportunity to talk today, and just wanted to take this opportunity to share my work that was done as part of my research work during my academic career and also during my professional experience in the jetting systems world for the microelectronics application. So today I'm going to focus on talking about the development for nanoliter and microliter depositions of adhesives, and also how the sustainability of the fine volume adhesive jetting plays in the microelectronics application here. So this is going to be my agenda for today. I'm going to spend some time talking about recent market trends and product trends in the medical microelectronics and implantable devices industry, followed by recent trends in the electronics packaging and PCB assembly. I think it's very important to kind of reflect upon where the trends are for the next 10 years and what drives that for companies in terms of manufacturing and assembly requirements, and then focusing towards the need for adhesive dispensing and review jetting systems with some applications to give a perspective of the needs and the research work that was done on fine volume depositions at conclusion here. So if you look at the medical implants market, there is a projection of growth in the medical implants and also microelectronics market for the medical industry from 26 billion in 2018 to almost 54 billion in 2026. That's a 9% growth that is being predicted. When we talk about medical implants, what are the medical implants here? They are pacemakers. They are heart pumps that are used for treating cardiovascular diseases. There are neurostimulators, which are used for treating Parkinson's diseases. There are implantable drug pumps that are such as insulin pumps that are used for diabetes management. So there are a broad range of different applications that are being there has been constant innovation and development to treat different types of diseases for the human body. Some of the companies that are being leading this whole medical implants innovation is like Medtronic, Abbott, Boston Scientific, ST Microelectronics, Connectivity, and many more. And just to give a perspective about how the growth looks for the microelectronics medical implant market, clearly there is a growth seen from 2014 to 2025 in different sectors, which are pacemakers or neurostimulators, implantable drug pumps. By regions, North America and Europe dominate in terms of the growth, and followed by Asia, Pacific, and Latin America. And here is another market trend that's been shared recently about growth in medical electronics. All medical electronics, it could be not just implantable, it could be other components, it could be batteries that are also being used from 2017 to 2025. So a 4.6% growth rate is being predicted there as well. So it looks like the market is growing and trending in the right direction, and there is an upcoming demand for these kind of niche products that are being used. As many of us know, pacemakers are implantable devices. They're introduced in the heart to treat abnormal rhythm of the heart itself, and it's controlled with electrical impulses. It has a dual functionality of pacing and sensing. Just to give a perspective of how the dimension of a pacemaker and how big or how small it is, I mean that's your human body heart, and that's the size of a pacemaker. As you can see that this is as the size of a dime itself. So that tells us the scale of miniaturization of components or microelectronic components, printed circuit boards, and other active and passive components that are being used to make this device itself. Some of the other latest products that Medtronic has been leading the way here is their own pacemakers. So they have the traditional pacemakers, which are lead-based pacemakers, and they're used for pacing and sensing, as shown in this figure here. So you have a subcutaneous pocket where the module sits, and then it's driving into the heart for electrical impulse for pacing and sensing. To give a cross section of this whole system, the module itself, you can see you have a highly densely populated circuit board substrate here, fairly smaller in size and dimension, and a battery here for power generation as well. The next generation of Medtronic pacemaker, which is called the Medtronic Micra, and that's now the world's smallest pacemaker that's available on the market. You can see it's a completely new design as compared to the old generation product itself. It's not a lead based, it's a leadless pacemaker, or they also call it as a transcatheter pacemaker. It doesn't have any subcutaneous pockets on the human body, it just goes straight into the heart and is acting as a pacing and sensing dual application as well. And looking at the cross section of this itself, of this micro pacemaker, you can see the size of the electronic modules and the electronic board itself. It's the dimensions are significantly smaller as compared to the one that's shown in this figure above, and with other components here. So that's where the trend is being towards miniaturization, and I think this gives us a good perspective to kind of see what that miniaturization looks like when you talk about smaller and smaller components here. For other applications like insulin pumps, I mean, here's a good examples of showing what an insulin pump cross-section looks like, or teardown looks like. You can see the circuit boards that goes in with different cell batteries that's used to be attached to the human body for pumping insulin itself. Fairly a smaller sized product here with the insulin pumps. So obviously very vastly in demand, and Medtronic is also leading the way for making different insulin pumps here. Now, talking about technologies and microelectronic trends outside of medical device. With the existence of 5G technology in consumer devices, the industry is certainly towards small form factor technology itself. With what that means is everybody wants to have a really small real estate on the printed circuit board with highly densely populated components, and that will give supreme electrical performances, and and also use passive embedded technology as well. So with that drive from going from 2G technology to 5G technology, of course, it comes with requirements from the OEMs for high I/O counts, complex package types, low power consumption, and so on and so forth. Um, and this is an example, a classic example of a smartphone circuit board. I mean, you can see that the real estate of the circuit boards have reduced, and the density of components have exponentially increased there. And just to give a perspective of 5G package itself, or a processor itself, you can see here a system in package where there are so many other microelectronic components that are being assembled here as well. Um, the new reports that have come out on retail and sales, and I think there's also new reports, and we've been just talking about it, that the whole market of the semiconductors and electronics is being going up, and which is good for the industry, because there is a demand issue, and because of the demand issue, the supply is going up as well. So certainly the projections are much higher for the US consumer electronics market, and smartphones are certainly leading that way, somewhere around 70 billion market, and followed by laptop, PCs, TVs, and other smart home devices here. So looking at the trends here for the non-medical device industries, for consumer electronic industries, both, and also for medical device industries, certainly the market is trending towards the increased scale direction, which means that it's not slowing down in terms of the needs of the OEM companies here. I also wanted to share some more information of new products that are coming as implantable devices, in the medical device space. Abiomed is a company, it used to be my previous company. They make products that are used for heart pump technology. So outside of the world of pacemaker and insulin pump, these are all catheter-based products that are used for treating cardiovascular diseases. Like this Smart Assist heart pump that's made by Abiomed is basically used for the blood flow inside the heart itself during surgical procedures or during cardiovascular shock, that can reduce the stress on the heart itself. Then there are some, Medtronic is also innovating and making products such as the drug-coated balloon pumps, which are used for again heart treatments, embolic protection products that are used for cerebral or brain-related treatments as well. So these are some of the other catheter-based products that are also termed as implantable devices that's been widely used in the industry. So looking at the trends, what the problem statement that we have here is, I mean, obviously with the market trends and with product dimensional trends, we see that there is miniaturization, there is high density component packaging, there is high complexity of the design and layout itself. Market is growing strong, which indicates need for more products. That means high volume manufacturing, high volume assembly of devices, also with high quality. I mean, quality has always been the number one in the medical device sector. What are OEMs looking for in high volume manufacturing, or processes that are being introduced for high volume manufacturing? They're looking for high throughput. They're looking for robust performances of the process over time, because in production, you're going to be running process day in and day out. So therefore, they want to have a robust process performance there. You're going also with innovations, there is going to be complex designs with different materials, form factors. So therefore, using traditional assembly techniques of welding and clamping and riveting, that's not going to be feasible, or it's not designed for manufacturable for using traditional techniques. So therefore, companies are looking for different ways of assembling. And also with medical implantable devices, one has to understand how the product is going to perform at different challenging conditions, like the complex loading conditions when introducing it into a human body, the wet fatigue environments into a human body when you introduce a pacemaker or any other device. So those are some of the other considerations that needs to be taken into account for the product that's being manufactured. Um, Adhesive bonding as a alternate solution towards mechanical joining is a promising solution because it's able to address a lot of the requirements and able to address a lot of constraints for assembly. Dispensing and jetting is also always looked upon as a reliable mechanism to deliver adhesives, especially in a complex design and a complex product layout. And as part of my work here, when I looked at previous literatures towards addressing miniaturization or high density packaging with dispensing or jetting process, a lot of literatures speak about mechanical systems towards nanoliter depositions. However, there is not much information out there that talks about how a process has been developed using techniques like design of experiments or screening analysis to get to nanoliter depositions. What are the process parameters or factors that can contribute to achieving those fine volume adhesive droplets? And also to add to that, there is also not much information about sustainability. I mean, is it real? Is it something that can be done over time? Is the process going to perform at the same level day in and day out? So there is a lack of literature there as well that we see. So jetting process obviously has been observed as a promising solution for adhesive dispensing or adhesive jetting. And for a high volume manufacturing process where you look for high throughput, um, OEMs are always looking at how many units per hour can be built by the process itself. So that is their metric to understand how fast that the process can run. Jetting certainly is by design a fast driven process than traditional dispensing, which are screw based dispensing system. So therefore that becomes an attractive solution for the OEMs to look towards jetting as a solution. Looking at cost of manufacturing, high speed process, sorry, will also reduce the number of equipments that are needed because these are run on typical fully automated machines. And companies are always looking to invest in having automated production lines, but also are very cautious about it because if they can have a process that can yield high throughput and can run faster, they don't have to invest a lot of money in buying a lot of equipments. So that's a big factor for companies. Droplet size capabilities are something that's always been characterized with the jetting process way back 15, 20 years back. I mean, this article back in 2005 have spoken about, what are the capabilities of using a dispensed jet, you can getting a droplet size of 300 microns as compared to using some other technologies. I mean, if you want to get less than a 300 microns droplet, you could use an inkjet system, but of course it has a limitation of running low viscous material. So this is still evident even today, to understand the capabilities of this jetting fine volumes along with different viscosity of adhesives that are available in the market for different applications. So it's a very important slide I see because the trend has still been consistent over the past 20 years. To understand more about the concept, jetting is a positive piston displacement concept. It's basically a simple upstroke and downstroke motion of a piston using a drive system. It could be either a linear motion, it could be a voice coil driven drive system, or it could be a piezoelectric drive system. With its upstroke, it's able to pull in the fluid that's required to be dispensed or jetted, and with the downstroke motion, it's able to eject the fluid at high velocity. There are all the different types of jetting, which is a contact style jetting or non-contact style, where you have a piston that comes in contact with the nozzle to eject the fluid out, and a non-contact style where you're just driving the material fluid out of the nozzle itself. So so that's a brief overview of what a jetting system would be in a nutshell here. For any process, there is always material considerations and what kind of adhesives can be used, and I think adhesive material considerations are very important for understanding what is the application, what is the product, where it is being used, what is, so based on that, different material considerations are looked into. I mean, here this table kind of highlights some of the commonly used adhesive materials like the cyanoacrylate material, or epoxy materials that are used for different applications. Like cyanoacrylates are used for catheter-based components, like some of the implantable devices that I showed you before, which are catheter-based components. They use cyanoacrylate for bonding applications or for coating applications. Of course, it comes with different restrictions or limitations there as well. Epoxies, are also used for some other types of applications, like coating, conformal coating process as well. And polyurethane are some other adhesives that are also looked into as well. Of course, for any printed circuit board typical assembly, you always have solder paste, deposition, whether through dispensing process or through screen printing process, depending upon the scale of the printed circuit board. So some of the applications of adhesive dispensing or jetting in in implantable devices are like, here's an application of a pacemaker where they have to coat this area here using an RTV silicone material. And the basic requirement is to coat so that there is no fluid ingress into the electrical components. Adhesives such as epoxies for encapsulation or 1-part or 2-part silicone adhesives can be used here. Looking at the drawing and looking at the design, you're looking at around 100 to 300 micron keep out zones, or 300 micron droplet size with keep out zones or less than 200 microns as well. Some other applications here are like this one here, which is highlighted in the figure 15. Is also for a pacemaker for bonding of components like batteries and electronic modules. And the need for this is basically to withstand high thermal excursions and have the components in place, which is very critical. Again, 2-part epoxies are very commonly used for this kind of application, and your droplet size are again around 200 to 300 microns here, with no contamination or no excess material around as well, as part of the requirement. Some other applications that I've dealt with directly are like UV coating applications using an UV material. Typically, Henkel is one of the leaders of supplying UV blazed adhesives that are used for coating of passive components here. This module does not go into a human body. It stays out of the human body because it provides the electrical power that's needed. But having said that, the whole product goes through additional assessments like sterilization, endotoxin assessments, biocompatibility assessments, so that that's also part of the product qualification requirement. So it's definitely important to make sure that the process is high quality. The glue that is used is also is compatible to the medical device requirements. So Loctite 3321 was the material that was used here. That's a Henkel based adhesive glue, the key requirement was for conformal coating application of passive components, and also covering some of the soldered wires here to make sure that there is there's protection from dust, contamination, or any mechanical loads as well. Some other applications here is like a gasket and sealing application. It's one of a very common typical dispensing application where you try to dispense and apply adhesive for sealing the bottom half of the handle of the bottom half of this case with the top half of the case as well. So that's done with a gluing process, along with what we saw on the previous slide about UV conformal coating application. This other one is also very interesting here, as shown in figure 18. So laser welding is one of the commonly used processes in in medical device manufacturing, basically used for joining process, and as part of the assembly post laser welding, the requirement is to do coating of the weld seam itself, so that would prevent any exposure of metal surface or any sharp metal surface that can cause complications to a human body or to a patient. Materials from companies like Epotech are used for doing coating applications to cover the weld seams here. Also here on top, you'll see Dello, which is a European-based company that provides adhesives for for gluing process itself, and which are biocompatible materials, and this goes straight into the heart. So therefore, it is very critical in terms of making sure that the weld seams are fully covered and not over and there is not excess material that can cause other problems as well. So one of the other critical applications for dispensing. This is for a balloon pump where it's required to perform a UV cure adhesive dispensing process inside this module, and that's used also for gluing application using a UV material. And this whole hub is called lures, which is basically pressurized for the use of a balloon pump. So this is another dispensing process that's being performed here as well. Okay. So the research work that was done with two different systems. One is a SST jetting system. That's a system that uses a non-contact style jetting and uses a voice coil driven jetting system, and the NanoShot, which is a contact style jetting and that uses a piezoelectric jetting system. So two different technologies that are used for evaluating, what are the fine volume deposition capabilities with the two systems here. So speaking more about the contact style jetting, it's a piezoelectric driven system with a stack actuator that will drive the piston inside the fluidic module and will come in contact with the nozzle in the end to dispense or to eject a fluid out. Um, Typically, the travel of the piston is very small, but the frequency is pretty high. That means the process can be very, very fast. So this pump has the ability to run up to 500 hertz. There is less wear of contacted parts because they're made of carbide material. It's a very promising system for fine volume jetting because it can run at very high speeds and it can also dispense very nanoliter scale droplets here. So it's a patented system and it is, it's developed by ITW EAE, the Camelot group itself. So to understand both the systems, my work had used design of experiments to kind of do a screening analysis and understand what are the factors that can contribute towards controlling the process and giving microliter or nanoliter depositions here. So it's just an overview of all the input factors and output parameters from the process itself for the jetting system here. So a split plot DOE model was considered. A split plot model is basically used when you have certain parameters that are not easy to change in the experimental study. Such as if you are trying to introduce different types of nozzle design, or if you're trying to introduce different piston designs. It's not something that you can randomize the experiment and keep changing in and out for every run. So those are called as hard to change factors. And some factors which are like software based factors that you can just enter a value and change, that are called as easy to change factors. So a split plot model in the DOE takes that into consideration to understand the experiment, where what factors are not easy to change and what factors are easy to change, so that it randomizes the experiment appropriately. Certainly fractional factorial model is also used, because it also helps to reduce your experimental trials and saves time and also give you high accuracy in your results using fractional factorial model here. So with the DOE analysis was done, this was an example that was done with underfill adhesive. Underfilling is a very common process or very typically widely used process in SMT assemblies. And this one was done for evaluating mass per droplet as a response. When the experiment was run, it was identified that the stroke of the piston, which is also called as the charge, and the air pressure, which is the pressure that drives the fluid into the fluidic module, are very significant. So higher the fluid, meaning more mass per drop. Higher the pressure means more mass per droplet, and higher the charge means more mass per droplet as well. There are also some interactions of nozzle size with the piston stroke and the nozzle size with air pressure that was also observed. So those were some of the key conclusions, and some hard to change factors that also were proven to be significant is the size of the piston. So the bigger the size of the piston, the more you're able to have the momentum to drive the fluid. But also depending on the viscosity of the fluid, you may get more mass per droplet, or you could get lower mass per droplet if it's a higher viscous material as compared to a lower viscous material. Nozzle size also played a critical role here, so therefore piston and the nozzle size very important in this jetting system. And there was also some interaction seen as part of the DOE. So just to give a perspective of all the factors that you can think about in a process when you're using a jetting system and what are significant to control or to get you what the mass per droplet is required. This is a table that gives a snapshot of it. To understand what are significant factors and what are not significant factors. And those are like the main effects plot coming from the DOE as well. So what were the conclusions? Nozzle type was not significant, which is very critical because in a jetting system, you could use or you could have nozzles made of different materials. There are nozzles that are made of ceramic-based materials. There are nozzles that are made of carbide-based material. There are nozzles that are made of steel-based material. Now, if you're going to be using or if you're going to be making a lot of these systems, using a ceramic nozzle tends to be more expensive. Especially in a high volume manufacturing environment, when you're using a ceramic nozzle, by nature it's very brittle. It's easy, it's very difficult to handle. You could break it, and it is expensive as well. So therefore, a steel-based nozzle or a carbide-based nozzle proved to be much more robust and more effective in terms of using as a nozzle type. Piston size, like I mentioned, was significant because that impacts the momentum that it gives to drive the fluid out of the jetting system to eject the fine mass per droplet. And after the DOE, there were validation runs were done to kind of validate with the settings to make sure that we were getting the right response. And also, a response optimization study was also done to predict what kind of mass per droplet can be obtained by certain parameters of the process. So these are some of the conclusions that was done, and these are all published. I'll show in my later slides the papers that I've published that you guys can refer to as well. So to understand with all these studies, what was the true capability? So here's the true capability of some of the fine volume adhesive depositions that can be done with the jetting system. So for an underfill adhesive, you can get as small as 0.01 milligrams per droplet, and that's about a 400 microns diameter of a droplet itself. In this study, I had also introduced quality because for an OEM, when they're looking at evaluating jetting systems for applications, they also look at quality of the droplets, quality of the dispensed patterns, because you have constraints like no contamination, no spraying, no trying to deposit excess material. So this study introduced that as a parameter or as one of the outputs for the DOE itself, where dot quality scaling was created based on inputs from subject matter experts. Some other adhesives like surface mount adhesive and encapsulants, they are a little higher viscous material, so they don't spread as you dispense on the substrate, and you could get droplet sizes as low as 250 microns, and they are also close to 0.014 milligrams per droplet. So very, very, very fine mass per droplets are able to be achieved using this jetting system here, and getting diameters as small as 250 microns. So just to give you a perspective of how these droplets look, as you can see here was a pattern of droplets with encapsulant adhesive. which is a slightly higher viscous material than underfill adhesive. Some of the typical dispensed patterns that are being used to cover components or for bonding application on substrates. This is a UV glue dot matrix that was also dispensed for the microliter and nanoliter depositions. Now, with the DOE, one can prove, or the DOE, the work has proved that yes, you can achieve nanoliter scaled volumes and you can achieve very small droplets of 250 microns. But the key question is this process of fine volume jetting sustainable in production? Because when you talk to OEMs, when you show them the process, the question is how sustainable this is going to be in production. Is this even real, that if I run in a production for several hours, for several days and years, am I able to get the same through results? So therefore process sustainability is a very key aspect of it. What this research did, or what this work did, was you try to use some of the quality control techniques like process control studies, which are like X bar S studies or X bar S chart, that is basically trying to look at with the best settings of the process and with the optimal output that we can achieve, are we able to run a production simulation and able to get the same response over time? So an X bar S chart was adopted. It's a commonly used quality control chart in the manufacturing industries. In this case, both the systems were used to do an encapsulant material was used for jetting application. Runtime was 12 hours, which is basically a typical day of production. And data was collected every 30 minutes to kind of understand how the process is performing over time. And sample size of 10 with subgroups of 25 was collected for the X bar S chart here. The responses were the mass per droplet, like how many milligrams per droplet was being dispensed, and also the droplet size. So here is your X bar S chart for the mass per droplet that I'm showing here. I mean, typically the process, one would say, well, the process doesn't look in control, but that's because you see a lot of red points here, and some of these red points are because of the run rules that you apply. But if you look at the process, you're having variations between 0.0115 and 0.012 milligrams. That variation is pretty small in terms of the performance of the process. So, although from a statistical standpoint, one would challenge and say that, well, the process does not look to be controlled, you have to also look from an applications perspective to kind of understand, is this sufficing to what the application requirements are? And maybe beyond process control, you also do process capability studies to understand what the requirements are and what the specification is and how you're performing against the specification rather than control limits. But also, one of the good things that was seen, or one of the really good things that was found, was running it for 12 hours. We was also able to trend the dispensed patterns to see how the dispensed patterns looked over time, and they looked very consistent in terms of how the droplet quality was, how the mass per droplet was also coming out. So that gave high confidence to say statistically that the process was validated to run in a typical production environment for almost 12 hours here. So some of the conclusions, the nanoshot technology, which is a piezoelectric driven system, was proven to be a high potential solution to address some of the manufacturing challenges of miniaturization because of its ability to dispense very small droplet size, as small as 250 microns, as we saw. Certainly process control studies are applied here to kind of look at how controlled the process can be in production over time. And the literatures that I had published also talks about other jetting applications like conformal coating with UV adhesives or surface mount glue, and how they performed as well. I would like to thank ITW EAE, Electronics Assembly Equipment Group, who kind of supported this research work, and along with SUNY Binghamton. It's been a big part of my research work, working with their systems and their innovative designs here. Here are some of my references. And here are some of the papers that I published on the work that I've presented here as well. Thank you. Any questions?
Thank you, Rajiv. I actually did have a couple of questions.
Yeah.
I noticed that you discussed a lot of applications of the jet dispense on a variety of medical devices. But when you were focusing on the jet dispense, you were sort of focusing on um, specific applications that would be involved in the circuit board assembly. Did the same study apply to both?
Yes, because encapsulant adhesives, although I had shown here was used in the surface mount assembly, they are also used in implantable devices, and they're
Uh,
also used for coating and bonding application. Now, the requirements of how small a droplet is needed is also along the same lines, because it depends on the scale of the component. It depends on how tight the area is to apply and how accurate it has to be. So I would say, even though it shows on the circuit board, it is equally applicable in the medical implantable assembly.
I see. And although circuit board is that was sort of the recognizable part of all of the medical devices. Um, Aside from that, they were all kind of unique. Is there any
Mhm.
commonality, like in the adhesive jetting or any other part of the assembly, or is the ultimate final packaging all sort of developed from scratch for each type of device?
Yeah, because every product, there is a design variation depending on what the usage of the product is. Some products, if you're going to have a product that's used in a heart, it there are different. Like a pacemaker is going to be different than a heart pump, because it both have two separate, completely different functionality. And both the way they're used in a human body is also completely different. So the process has to be kind of almost redesigned, because the product, the way it's used, is completely different from each other.
I see.
So
Is there any commonality in the equipment that's used?
equipment, I think there is a huge amount of opportunity for medical device industries like Medtronic to kind of explore more on the automation side of equipment to be used, because a lot of companies that I've seen still kind of fall back on handheld dispensing.
I
Uh,
see.
and I think that's where the push is to kind of bring in more towards automated dispensing and automated jetting, and understanding or establishing that confidence to say that this can be done much faster and much accurate, rather than using a manual labor to do some of the dispensing application.
I see.
And I think that is going to take time, but slowly companies are starting to look into that direction.
Okay, so this is something that um, uh, say assembly equipment companies might want to step up to.
Yep.
All right, interesting.
Yep.
Uh, any other questions?
Yeah. Well, thank you very much for the time, gentlemen, for this
Okay,
opportunity.
and thank you, Rajiv, for preparing the presentation and presenting it. And it will be posted online, the recording and the presentation slide set.
Thanks, Rajiv. Excellent talk.
Thank you.